Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on graph theory, lecture number 25, in which I will discuss on spanning trees. Before defining spanning tree, I will try to give you the concept of spanning tree with the help of particular examples. We have a graph. This graph is connected. Here vertices are V1, V2, V3, V4, V5 and V6, and edges are E1, E2, E3, E4, E5, E6, E7. This is a connected graph, and here we have two circuits. Here circuits are V1, V2, V3, V1 and V4, V6, V5, V4. These are two circuits in this connected graph. If we delete one edge from each circuit, here we delete edge E5 and here we delete edge E1, then still this is a connected graph. Here we have deleted edge, but we have not deleted vertices. In the original graph, vertices are V1, V2, V3, V4, V5, V6, and after deleting one edge from each circuit, the same vertices V1, V2, V3, V4, V5 and V6 are present. We have not deleted any vertex, and this is a circuitless connected graph, and circuitless connected graph is called a tree, and this tree is called spanning tree. Earlier it was the graph like this. Here edge was E1 and here edge was E5. If we delete the edge E7 from this circuit and we delete edge E1 from these circuits, we get again a connected graph, and in this graph the vertices are V1, V2, V3, V4, V5, V6, same as it was present in the graph, and here we get circuitless connected graph. This is another tree. Since circuitless connected graph is a tree which contains the same vertices as the original graph, and it is a tree, and this type of tree is called spanning tree. Now we define the spanning tree. A tree T is said to be the spanning tree of a connected graph G. If T is a subgraph of G and T contains all vertices of G, the spanning tree T may be called the skeleton of original graph G. Since spanning trees are the largest tree subgraphs among all tree subgraphs in graph G. Therefore, spanning tree is the maximal tree subgraph or maximal tree in G, in graph G. As spanning tree is defined only for a connected graph because a tree is always connected, and in a disconnected graph of n vertices we cannot find a connected subgraph with n vertices. Each component of a disconnected graph may have spanning tree. Therefore, disconnected graph with k components has a spanning forest collection of all spanning trees of components, and therefore a disconnected graph with k components has a spanning forest consisting of k spanning trees. Now we prove a theorem. Theorem is every connected graph has at least one spanning tree. Now we prove this. Let G be a connected graph with n vertices. Case 1. If a G has no circuit, then G will be a circuitless connected graph with n number of vertices. Since circuitless connected graph is a tree, and also this tree will contain n number of vertices, that is same number of vertices of graph G. Therefore, G will be a spanning tree. Case 2. Let G contains a circuit. Since G is a connected graph with one circuit, and if we delete one edge from the circuit, the resulting graph will be still connected, circuitless. Having a number of vertices. Therefore, the resulting graph will be a spanning tree. Since when we delete one edge from the circuit, the graph remains still connected, and also it will contain same number of vertices as the graph G. So no vertices is deleted, and the resulting graph will be a connected circuitless graph. That is, the graph is a tree, and since it contains a number of vertices which is equal to the number of vertices in the graph G, therefore the resulting graph is a spanning tree. Case 3. Let the graph G contains some circuits. If we delete one edge from each circuit, the resulting graph will be still connected, and there will be no circuit, and the resulting graph will contain a number of vertices. When one edge is deleted from each circuit, the resulting graph will be still connected and circuitless, and it will also contain the n number of vertices, because we have not deleted any vertex. We have deleted one edge from each circuit. Therefore, the graph will be connected circuitless with n vertices. That means the resulting graph is a spanning tree. Therefore, the resulting graph is a spanning tree. So, we get at least one spanning tree in each connected graph. Therefore, every connected graph has at least one spanning tree. Proved. Now we will give the concept of branch and chord of a spanning tree with the help of example. Firstly, I will try to make you clear this. Let we have a connected graph. Here vertices are V1, V2, V3, V4, V5, V6. This is graph G. And edges are E1, E2, E3, E4, E5, E6, E7. if we delete one edge from each circuit, we get a spanning tree. Now let us delete edge E7 and E1. We get a spanning tree. Let name of this spanning tree is T1. Here edges of the spanning trees, edges of spanning tree T1, B, E2, E3, E4, E5, E6. These edges are called branches of the spanning tree T1. These are branches of spanning tree T1. We have deleted the edge E1 and edge E7, and edges E1 and E7 are chords of spanning tree T1. Now again we have graph G. Here we connect by edge E1 and here edge E7. Now we delete edge E6 and edge E2. The graph is still connected and the vertices are same as in graph G. So this will be a spanning tree, connected circuitless graph having same vertices of G. So this is a spanning tree. This is spanning tree T2. Edges of spanning tree T2 will be here E1, we have deleted E2, E1, E3, E4, E5, E7. We have deleted E6. And edges here E2, E2 and here E6. We have deleted these edges are chords of the spanning tree T2. As by deleting one edge from each circuit of the graph, of the connected graph, we get different types of spanning tree, because in circuit we may delete any one of the edge. So if first time if we delete a certain edge from the circuit, in the second time we delete another edge, we get a new spanning tree. Now we define the branch and chord of a spanning tree. Now we define branch of a spanning tree T. An edge in a spanning tree T is called a branch of the spanning tree T of the graph G. Now we define chord of a spanning tree. An edge of a graph which is not an edge of the spanning tree T is called a chord. Now we prove a theorem. Theorem is with respect to any of its spanning tree, a connected graph of n vertices and e edges has n minus 1 tree branches and e minus n plus 1 chords. Now we prove this. Let G be a connected graph such that number of vertices equal to n, number of edges equal to e. Let graph G has some circuits and if we delete one edge from each circuit, the resulting graph is still connected with n vertices. Let this resulting graph is T. Therefore, T is a circuitless connected graph with n vertices. Therefore, T will be a spanning tree. Since spanning tree is a tree, since it contains n vertices, therefore it will contain n minus 1 number of edges. As we know that if a tree contains n number of vertices, then that tree will contain n minus 1 number of edges. And these edges are tree branches of the spanning tree T. Therefore, number of tree branches equal to n minus 1. Since given that graph G contains e number of edges, therefore e minus n minus 1 number of edges have been deleted to form the spanning tree T, and this number be the number of chords. Therefore, number of chords equal to e minus n minus 1 equal to e minus n plus 1. Proved. Now we solve a problem. Problem is, let G be a graph of a farm consisting of walled plots of land shown in this figure, and let plots are filled with water. Find the minimum number of walls to be broken so that all the water can be drained out. This is the figure and this is a graph. This is a graph G. This is a connected graph. This is a connected graph having 10 vertices and 15 edges. Here this is a vertex, this is another vertex, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And similarly we may count the number of edges. This is one edge, this is second edge, third edge, and so on. Since it is a connected graph which contains some circuits, if we delete one edge from each circuit, then we get a circuitless connected graph, and that graph will be the spanning tree of the graph. So our aim is to find the chords. Chords means the edges of the graph which are deleted to form a spanning tree. If we delete one edge from each circuit of the graph G, the resulting graph will be T, which is connected circuitless graph containing 10 vertices. Therefore, T will be a spanning tree. Spanning tree is a tree. Therefore, T will contain 10 minus 1 equal to 9 number of edges. Therefore, number of edges deleted from G to form spanning tree T equal to our total number of edges in G equal to 15 minus remaining edges in spanning tree 9 equal to 6. So we delete 6 number of edges. So 6 number of walls will be broken to solve our problem. With the help of direct formula, we may also solve this, as number of chords equal to E minus n plus 1, E be 15 minus n is 10 plus 1 equal to 6. These chords are those edges of G, graph G, which are removed to form the spanning tree T. That is, 6 number of walls are to be broken to solve our problem. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.